Look here, this pen which I'm supporting with the 2 fingers here, okay, 2 fingers. That means I'm exerting 2 forces at these 2 points. Instead of exerting these 2 forces, I can choose one point. That one point will come almost somewhere in the middle like this. Okay, we know we can balance it like this at one point. With a uniform shape, exactly in the middle it will come. If you are taking a ruler, you might have many times tried it. A ruler, 2 ends you keep the finger, you can support it. Instead, there is another point, only one point.
Yes, sir.
That means exactly the center with a compass or any narrow point enough. You can just balance the entire body. It means suppose this is a ruler. Here you are exerting 1 Newton force to support this one. So it's weight acting downward mg. This effect, okay, this can stop this. I mean, keep the this one meter scale balanced. Now, instead of giving this 1 Newton here, suppose I am giving 1 point, that 2 Newton together. It can be balanced. It won't fall down. But any other point, if you choose, it will fall down. Because at this point, it's weight acting downward. So here, if you are exerting force, see, this will cause a rotation. So this point at which the entire weight of the body is concentrated is known as center of gravity. Or this point at which entire mass of the object appeared to be concentrated. Actually, it is not concentrated. That's an imaginary point. But that point, if we place a sharp pen, we can balance the entire body. That means that point on the object where entire body appeared to be concentrated. And at that point, if we give a total force, then it will be balanced. Or in other words, suppose this body, I am giving here 1 Newton force, 1 Newton force. This body is 1 kilogram body. It is moving with a speed, acceleration. That is F is equal to ma, A is equal to F by mass. F is 2 Newton, say mass of the body is 1. Instead of giving these 2 points, give the 2 Newton at this point. The body will go with same acceleration. That means instead of applying the forces at different points, altogether that force acting onto center of mass, that body will have same acceleration. So that point exactly behaving like the entire body. So this particular point is known as center of mass. And at that point, entire weight acting. So there, if you apply a force upward, that can be balanced. This point where entire weight acting is known as center of gravity. Is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Center of mass of a body is a point. Center of mass of a body is a point. Center of mass of a body is a point at which the entire mass of the body appears to be concentrated. Entire mass of the body appears to be concentrated. Next paragraph. Center of gravity is a point. If mass is concentrated at one point, gravity also will come there. So mg will act there. Center of gravity is a point on the body at which entire weight of the body is acted upon. At which the entire weight of the body is acted upon. Now let us see some activity of center of mass. Okay, you take a ruler. If you have a ruler at your home, you can take a ruler and see. Can you see this? Take this ruler like this and see 2 fingers. You hold it like this. Okay, keep reverse and hold it like this. These 2 fingers, and don't move this left finger. Left finger don't move. Okay, keep like this. and the right one, you move it towards it. See, automatically you can see this pen is adjusted. So that you see 2 fingers came to center of mass. So center of mass as a property of the entire body. It will behave like entire body. So you know the property of a body. Only if a force acting, it will have a change of state. If it's at rest, a force acting, it will move. Otherwise, body will never move. Here also, you see, I'm not touching center of mass. Center of mass is somewhere here. I am keeping my fingers here and trying to move this one finger near to the other one. So center of mass is not being exerted by any force. So automatically the system adjusted so that center of mass remain in the same place. So that either side will be adjusted automatically. You can try this. If you have a ruler, just hold in your hand and try like this. One finger don't move, other finger you try to bring near. Automatically the ruler will adjust and your both the finger will reach exactly at the center of mass. Try this activity. You can see that. Okay, again I'm showing you. See, keep like this and move your finger like this. See, now it's automatically adjusted. See, now 2 fingers reach at center of mass. As long as I'm exerting force onto center of mass will not move at all. Is it clear?
Yes, sir.
Now, next one, derivation. Center of mass of 2-particle system. Center of mass of 2-particle system. Center of mass of 2-particle system. Draw this diagram. Look here. Here one particle, that is M1. Position vector of this one is R1. Position vector means, you know, this will give you X, this will give you Y. So position vector is R1. And there is another body, M2. Position vector is R2. Now, if these bodies are equal masses, center of mass will come almost in the middle. If M2 is heavier, center of mass will shift towards M2. M1 is heavier, center of mass will shift to M1. This is the dotted line, okay, reference line. This point is center of mass, okay? And position vector to that center of mass is R. We are going to get expression for position vector to center of mass from origin. This is what we are going to calculate. Now write the heading, expression for position vector to the center of mass, expression for position vector to the center of mass of 2-particle system. This is the heading of derivation.
Sir, expression for position of?
Expression for position vector to the center of mass of 2-particle system. We are going to obtain expression for this R. Before coming to this derivation, 2 things you have to understand here. Look here. X is equal to position. Suppose X is given as 8t squared plus 3t plus 4. Then its velocity can be written as d by dt of X. Then we know this is 16t plus 3, isn't it? Tell me.
Sir.
Actually, which process you have done here?
Differentiation.
What is this process called? Differentiation, right?
Yes,
Yes,
sir.
sir.
Yes, sir.
So this is called first order differentiation. So first order differentiation of x gave you velocity. Now again I am going to differentiate it one more time. D by dt of v, or we can write this d by dt of dx by dt, or this can be written as d squared x by dt squared. So answer is this will differentiate again. That will be 16, isn't it? Because power 1 here. Any doubt?
No, sir.
No. So this is the second order differentiation. This is called acceleration. That means acceleration can be written as d squared x by dt squared. Here don't mistake, I have multiplied d into dt squared. It's not multiplication. It is 2 times differentiation. That means this is the value of x. When I differentiated first dx by dt, I got this answer, that is velocity. Again, when I differentiated, that is d squared x by dt squared. It means this value differentiate again. Then I will get acceleration. So this is called second order differentiation of position will give you acceleration. Did you understand that?
Yes, sir.
Anyone has doubt?
No, sir.
Oh. So that's the meaning of second order differentiation. Now don't think d into d we multiply. Now look, here I am exerting a force onto it. This is called external force. That is F1. Externally, I am exerting a force. At the same time, by Newton's law of gravitation, we can say this M1 is being attracted by M2. So we can say that F12. This is force acting on 1 by 2. This is known as internal force. Similarly, I am exerting a force onto M2. This is a force exerting onto M2, external force, that is F2. And here there is an internal force that's acting.
F21.
F21, force acting on 2 by 1. Force acting on 2 by 1. Here internal forces cancel out because they are always equal and opposite. For example, this is sun. Around here planets are there. Sun attract the planet and planet attract the sun, but they are not collapsing each other, right? They keep on revolving all around, isn't it?
Yes, sir.
These are known as internal forces. So internal forces get cancelled out each other always. Clear? So here we can say F12 and F21 will cancel out always. Now F1 and F2 produce a motion. Now by Newton's second law, applying Newton's second law to the mass M1, to the particle of mass M1. Are you right here? Did you finish the diagram?
Yes, sir.
Oh.
Yes, sir.
Let us consider, right introduction, let us consider the particles of masses M1 and M2. Let us consider the particles of masses M1 and M2. Having their position vectors, vector R1 and vector R2. Having their position vectors, vector R1 and vector R2, as shown in figure. Let vector R is a position vector to center of mass. Vector R is a position vector to center of mass.
Well,
Vector R is a position vector to center of mass. Okay. Here F12 and F21, F12 and F21 are internal forces between M1 and M2. F12 and F21 are internal forces acting between M1 and M2, and which are cancelled out each other, and which are cancelled out each other, which are cancelled out each other
Internal forces.
between M1 and M2, and which are cancelled out each other. Let F1 and F2 are the external forces. F1 and F2 are the external forces acting on the particles M1 and M2 respectively. Acting on the particles M1 and M2 respectively. That means F1 to M1, F2 to M2.
Sir, are external forces?
Acting on to M1 and M2 respectively. Okay, now write. Applying Newton's second law, applying Newton's second law to the particle of mass M1. Applying Newton's second law to the particle of mass M1. What is Newton's second law? F is equal to ma, right? So here total force acting on the particle M1 is F1 plus F12. That's equal to mass into acceleration. Here acceleration I am giving in second order differentiation. D by dt squared of x. R here, R1. D by dt squared of R1. This R1 keep changing.
Answer, it's M1, right?
M1 into d squared by dt squared of R1. So d by dt squared of R1 give you acceleration of mass M1. That's what that R is changing. Is it clear?
Yes, sir.
Yes, sir.
Similarly, applying Newton's second law to particle of mass M2. Similarly, applying Newton's second law to a particle mass M2. Total force is F2 plus F21 is equal to M2 into this R2 will keep changing. So d squared R2 divided by dt squared. Now the total force acting on the system F1 plus F12 plus F2 plus F21 is equal to M1 into d squared by dt squared R1 plus M2 into d squared by dt squared R2. Since F12 and F21 are internal forces, they get cancel out each other. Since F12 and F21 are internal forces, they get cancel out each other. Then F1 plus F2 is equal to d squared by dt squared into M1 R1 plus M2 R2. D squared by dt squared we have taken commonly out. M1 went inside, M2 went inside here. Now numerator and denominator multiplying by M1 plus M2. Then F1 plus F2 is equal to M1 plus M2 into d squared by dt squared M1 R1 plus M2 R2 divided by M1 plus M2. Numerator and denominator multiply by M1 plus M2. This is equation number 1. Okay. Any doubt? Any doubt up to here?
No, sir.
No, sir.
Now you see, what is the definition of center of mass? Center of mass is the point where if you are applying this F1 and F2 together, that R also will go with the same acceleration, right? Isn't it?
Yes, sir.
Sir, I didn't get it.
Center of mass means what? Instead of applying forces at different points, add all forces together and exert onto center of mass.
Yes,
Then
Yes,
sir.
sir. Yes,
effect
sir.
will be same, right?
Yes, sir.
Now, that means total force acting on the center of mass is now F1 plus F2.
Yes, sir.
What is the mass of center of mass?
M1 plus.
M1 plus M2. Yeah.
Yes,
Now
sir.
applying Newton's second law to center of mass. Their forces we are exerting F1 plus F2. Now mass of the center of mass is M1 plus M2. Okay. Then d squared by dt squared, position vector r is accelerated. Now r. Equation number 2. Any doubt? Applying second law to center of mass. So total force F1 plus F2 we are exerting to center of mass. At center of mass, total mass is concentrated. That means
Yes,
mass
sir.
of the center of mass is M1 plus M2.
Yes, sir.
Its position vector R. So it's accelerated d squared by d
Yes,
squared
sir.
R. Yeah.
Yes, sir.
Equation number 2. Now equate 1 and 2. See left side F1 plus F2, F1 plus F2. M1 plus F2, M1 plus M2. Here vector R is equal to this one. Okay. So here vector R is equal to M1 R1 plus M2 R2 divided by M1 plus M2. See, this is a formula for position vector. So usually we all think M1 plus M2 by 2. Like that we can get position R. But it's not like that. It is a weighted average, but weights are being attached to the end of position
Here
vectors.
we are dividing 1 and 2, sir.
Dividing?
1 and 2.
No, we are
Weighting.
comparing.
Okay, sir.
Comparing
I got
1 and 2. See here F1 plus F2, F1 plus F2. Same thing, right?
Yes, sir.
M1 plus M2, M1 plus M2. D squared by dt squared, d squared by dt squared. Here instead of R, this portion will come. Isn't it?
Yes, sir.
So comparing 1 and 2.
Yes, sir.
It's an important derivation, okay? Now you got this formula. This is the formula for position vector. Now let us write about this position vector. That's equation number 3, okay? This equation number 3. Right now. Equation number 3 shows that equation number 3 shows that equation number 3 shows that the position vector of the center of mass can be taken as position vector of center of mass can be taken as weighted average. It is not just an average, it's a weighted average of the position vectors. Weighted average of the position vectors. And the weights are being attached to the position vectors. Now look, here
Sir, what is weighted average?
and the weights are being attached.
So what is weighted average?
This is known as weighted average. This formula is known as weighted average. It's not just an average. It's not M1 plus M2 by 2 or R1 plus R2 by 2. It is the weighted average of position vector, and M1 and M2 are being attached to the end of it. Now look, this yellow line I have marked, M1 to M2. Okay, that is a connection between this M1 and M2. Okay, imagine a line. Center of mass will come on that line. Now this line, okay, center of mass. This point of center of mass I am bringing to where? Origin. Now this is a center of mass. This one I am bringing to origin. This is a center of mass. Then what is the value of R, position vector of center of mass?
0.
0. Now center of mass is at the origin. So distance to center of mass is now 0. But now M1 is here, right? This is M1. This is M2. That is not 0. That is still origin to M1 is R1. Origin to M2 is R2. Isn't it?
Yes, sir. Yes, sir.
So substituting here, if center of mass is assumed to be at the origin, if center of mass is assumed to be at the origin, if this center of mass is assumed to be at the origin, then position vector R becomes 0. Therefore, M1 R1 plus M2 R2 is equal to 0. Because this one, if you are taking to left side, that also will be 0.
Sir, position vector can be? Position vector.
Read the full sentence.
If the center of mass is assumed to be at the origin, the position vector
Of center of mass is 0.
Okay, sir.
Did you understand how it will be 0?
Yes, sir. Yes, sir. I got that.
Then M1 R1, this formula. Look here, R is 0. Therefore, M1 plus M2, if you are taking left side, product will be 0. So we can write M1 R1 plus M2 R2 is equal to 0. Or M1 R1 is equal to minus M2 R2. Then R1 is equal to minus M2 by M1 into R2. If M1 is equal to M2, then R1 is equal to minus R2. That's what, if a uniform body, suppose here 10 kilogram, here 10 kilogram, then position vector will be exactly in the middle. Then R1 will be equal to R2. Otherwise, it depends on ratio. If this is 20 kilogram, substitute 20 by 10. Then position vector will shift to this side. Is it clear?
Yes, sir.
Yes, sir.
Now, center of mass of n particle system. N particle.
Sir, can you reverse, please? Can you go back? Thank you, sir.
Center of mass of n particle system. There are n particles. Right. That means there are many particles here. This is M1, this is M2, this is M3, M4, then where the center of mass will come. That depends on mass of this object. Clear? That's what. How will you find out? Center of mass of n particle system. Let M1, M2, M3, Mn are the particles of a system, having their position vectors R1, R2, R3, Rn. Having their position vectors R1, R2, R3, Rn respectively. Then center of mass can be written as M1R1 plus M2R2 plus M3 R3 divide MNRN divided by M1 plus M2 plus MN. This is a position vector of center of mass for any particle system. This is also a weighted average. See M1R1, M2R2, M3R3 like that. Next, have you finished?
Yes, sir.
Yes.
Yes, sir.
Velocity of center of mass. Right. We know R is equal to M1R1 plus M2R2 divided by M1 plus M2. This is RCM, center of mass. M1 plus M2. Now let M is equal to M1 plus M2. Therefore, RCM is equal to M1 R1 plus M2 R2 divided by M. Then M into RCM is equal to M1 R1 plus M2 R2. Differentiating M into d by dt of RCM is equal to M1 into d by dt of R1 plus M2 into d by dt of R2. Then M into d by dt of R is velocity, right? Differentiation of position vector is velocity. M1 into this velocity of the first particle, V1, plus velocity of the second particle, V2, M2, V2. Therefore, VCM is equal to M1 V1 plus M2 V2 divided by M, or VCM is equal to M1 V1 plus M2 V2 divided by M1 plus M2. See, same thing. Here R, here just replace V everywhere. Okay?
Okay, sir.
This is the velocity of center of mass. After completing it, tell me. Only less than 1 minute. It's over this one.
Yes, sir.
After
Sir.
this, you write acceleration of center of mass. Okay, that's the next heading. You just tell me that start. Acceleration of center of mass.
Okay, sir.
Can I wind up? Now it will be off.
Yes, sir.
Sir, acceleration of center of mass.
Next heading, acceleration of center of mass.